Chapter 2, Atoms and Elements. So, many of you have a pencil. Look at the end of your pencil. It's made out of graphite. If we took that piece of graphite in your pencil and cut it in half, and took one of those halves and cut that in half, and just kept doing it, could we go on cutting it in half forever? Or would there be a point at which we came to a piece that could not be cut in half? What do you think?
Like realistically or hypothetically?
Hypothetically. Because obviously there would get to a point where it was so small you can't see it, right? And it would be narrower than the knife you were trying to cut it with. That would be a logistical problem, but theoretically. Well, it turns out that eventually you would get to a point where you get to something that was an atom, a carbon atom, and you would not be able to cut that in half. The word atom comes from the Greek word atomos, meaning indivisible. So the idea here is that matter is composed of smallest particles that cannot be cut in half. Matter is not infinitely divisible. You take that carbon atom, we know that we can use nuclear chemistry and blast that atom apart, but it's not carbon anymore. Cutting something in half is a physical change where you just have smaller pieces of the same substance. When you get down to the atom level, you can't cut it in half and still have the same substance. Everything's composed of atoms, and so if we want to understand how matter acts, its properties, its characteristics, then we have to understand how atoms behave. Okay, so back in 1827, a guy named Robert Brown was looking through a microscope at water-suspended particles that had come from pollen grains. Okay, and I found a YouTube video here that actually shows what the same thing he was looking at. So let's see if we can play this. So you see these little particles? These are water-suspended particles from pollen. So those particles were wiggling, right? Why?
Well, if you have kids, your first guess would be sugar.
Yeah. If you have kids, your first guess would be sugar. That's what makes children wiggle, right? Kids have lots of extra energy. Children are alive, right? Are those little particles alive? They looked like they were alive, right? Stuff that moves must be alive. Well, not necessarily, because you could hang pieces of tinsel from a tree and the wind will blow them and they move, but they're not alive. So Robert Brown initially thought that these particles might be alive, but then he did some more investigation and realized, no, they're not alive. The source of the motion then can't be from the particles themselves. It must be something from the outside, something perhaps in the water. So in 1905, a little bit later, Albert Einstein came up with a theory that explained this motion that Brown had observed. And this movement of particles, that jitteriness, is called Brownian motion after Brown. Albert Einstein says that that is a result of molecular bombardments of the particles due to the thermal energy of the surrounding water. So we talked about how particles, atoms, and molecules in a substance are in motion, right? So in a liquid, the particles are actually sliding past each other, like the students in a classroom when we get up and move around during lab. So what's happening to those little particles is that the water molecules are moving and are hitting the particles. The particles are large enough that we can see them with a microscope. Water molecules are too small to be seen with a microscope. but you have enough of them wiggling around that they are hitting those pollen particles. It's a little bit like you throw a beach ball into a crowd at graduation, right? And people hit it and the ball bounces around in a very irregular fashion. It's the same idea. The water molecules are running into those particles and causing them to jiggle around. This was important because it inferred the existence of atoms. They're too small to see, and especially in 1905, there were no techniques that allowed us to image atoms. But this inferred the existence of atoms. And then Einstein's work and the work of others that went on removed any doubt about the particulate nature of matter. Before that, there were some doubts. People had questions. Do you have any questions? 1980s. Jump forward a bit. Two researchers at IBM in Switzerland developed something called scanning tunneling microscopy, STM for short. And here's a picture of it. You've got your probe here. I better use my stylus because my finger's wandering. You've got a tip here that's at the end of this instrument. And they pass an electric current from the tip to the surface. That's called a tunneling current. The amount of current that will flow, because it's jumping through air, is highly dependent on how far away from the surface this tip is. So what they do is they use a computer to move this tip to keep the current constant. And what that does is it keeps the distance from the end of the tip to the surface constant. And so basically you're feeling across, and if you come to a bump, the computer raises the probe and you can detect that. And it's just keeping a constant distance from the surface. Scanning tunneling microscopy is a technique that we can use to image and even move individual atoms and molecules. This image here is one of the Japanese characters, the two Japanese characters that represent the word atom. And it was written with iron atoms on a copper surface. So each of those little cone-shaped lumps is an atom. And they can be moved. So let's watch a couple other YouTube videos here. Okay, we'll do it this way. No. Try it this way.
So what we do to move atoms is a variation of what we do to see the atoms in the first place. So we can't use light to see them. So we're not looking through a microscope like the conventional microscope we're used to. We need something that can see much smaller things than that. So what we do is take a sharp metal needle and bring it close to the atoms. And in a sense, we're feeling the shape of the atoms. So if you imagine that we have a surface that we're putting an atom on, we put it on a surface so it holds still. What we do is take this metal needle close to the atom and sense its presence by measuring an electric current that flows. And as the tip of this needle approaches the atom, it sees more electric current, and we draw it up and over the atom to keep that current constant. So in a sense, we're feeling the shape of this atom. Then in order to move atoms, we observe that we have a sharp metal needle near it. We can bump into it by accident. What we can do is, instead of doing it by accident, do it under control. If this is our atom on a surface, we can move the tip close and we start to form a chemical bond between the tip and the atom. And that chemical bond forms between most atoms. They like to bond to each other in most cases. So we start to form a bond such that the atom follows the tip around on the surface. We can drag it to a new spot. When we withdraw the tip, it holds still because the surface is holding it in place. And we can take an image and see where we've placed this atom. So that process, repeated over and over, is how we've built most of the structures in our lab. That's our bread and butter basic technique for moving atoms around.
Any questions? They actually use this technique to make the world's smallest movie. It's not very long, and I think it's kind of neat, so we're going to watch that too. So they used scanning tunneling microscopy and stop motion animation to create that little movie by moving atoms on a surface. There's another video, it's a little too long and not as instructive, that shows how they did that, and I will put that on the playlist as well if you want to look at that. It's kind of interesting. Any questions? These are the best sorts of images that we can get of atoms. They are not actual pictures. They are caused by us basically feeling for the atoms. And so that's why they're kind of cone-shaped and fuzzy. Actually, we believe that atoms are spherical and not little cone heads like that. So just to give you an idea of how small atoms are, have you heard of the Library of Congress? It's in Washington, D.C., I believe. They have 35 million books on 840 miles of shelving. Can you imagine? A bookshelf 840 miles long. So if you took all the words in all of those books and wrote them in letters the size of those kanji characters, all those words would fit in an area of 5 square millimeters. That's half a centimeter on a side. All the words in all the books in the Library of Congress. Atoms are crazy, crazy small. They are the connection, though, between the macroscopic world that we can see and microscopic worlds and submicroscopic. So an atom is the smallest identifiable unit of an element. There are about 91 different naturally occurring elements, and there's over 20 synthetic elements. Those are ones that are not found in nature. And they've been adding and giving names to some of the newer ones. So any questions?